Alright, in this video we're going to look at Faraday's law and signals and really answering this question of how does electricity communicate information. So before, in kind of the last unit, we talked about how computers think, how we kind of organize information into ultimately ones and zeros. And so that's where we want to start here, is with reviewing really briefly why do we use binary with computers, or I guess the more accurate question, why is it useful? And if we remember, it's ultimately because there's two states, so a 0 and a 1. So anything that can be either one thing or another thing can code binary numbers. So I talked about at one point like a switch, so you imagine a light switch and it can be either up or that light switch can be down. And you could imagine a giant wall of these and you can flip them up and down and you can store numbers like that. A light bulb, for example, you can imagine that being, off or it being on, and that could also store information like that. So what we're going to do with this lesson is look at least roughly how electricity can be used to communicate ones and zeros. One thing I will say about this before we get too far into it, this is going to be one of the lessons where we're going to do very big overview, and in some sense, what I'm going to be telling you isn't technically 100% correct, but it does give you the idea, and if you wanted to learn more and get more involved with this, it would be really easy to correct kind of the lies, so to speak, that I might be telling you. And I'll do my best to identify something that's an oversimplification to the point where it's technically not true, but again, it communicates the big idea, and that's more what we're concerned with in this class. So before we get into that, we need to talk about some terms, just so that you have these in mind, and so when I use them, you know roughly what I'm talking about. So electromagnetism is our first word, electromagnetism, and that's the study of electricity and magnetism. So pretty self-evident from the name. It's just a combination of electricity and magnetism. It's the study of both of these things. Charge is the unit or the amount of, we'll say, electricity somewhere. This is something that's kind of a simplification, but if you want to think about if there's, when you think about electricity flowing through a wire, if there's a lot of electricity, that means there's a lot of charge, is what we'd actually say if we wanted to be more proper in our use of terminology. Current is how much charge is flowing through a wire or past a point or through a material. So charge is just how much stuff is there. Current is how much is flowing past a point. It's often likened to a river, where charge would be the amount of water, and the current is how much of that water is flowing. So you could have a large current because the river is really big and moving, even if it's moving kind of slow, or you could have a large current because it's moving really fast, even if it's pretty small. Because what we care about is the gallons of water flowing past a certain point for current. So next, voltage is how hard the charge is pushed or pulled through a current. So it's basically, if you think about that river with the water flowing through it, it's how hard the water is being pushed through that river or being pulled down the hill. So a higher voltage will tend to also mean a higher current, because if you're pushing harder, you're going to move more of that charge. Resistance is how hard it is for charge to move. So this is in some sense, you can think about it the opposite of voltage. If there's a lot of resistance, you're not going to have much current. And then lastly, power is voltage times current. So if you multiply your voltage and your current, you get power. It's a special technical term, and I'm just pointing it out because it's easy for people to kind of mix up power with some other things. I'm only highlighting this not because you really need to know it, but because I don't want you to think of charge or current or voltage as power, know that power is technically a separate word if we're going to use that. So if you're thinking about charge, or you're thinking about current, or you're thinking about voltage, use that word. All right, moving on. Now we're going to talk about Faraday's law, and it's going to be a big long thing, but I'll summarize it for you at the end. So if the magnetic field changes inside a coil of wire, that creates a voltage, which in turn pushes current or charge through that coil, which is also known as current. So if you move the magnet near a current of wire, or if you spin that magnet near a current of wire, you see that you create a voltage, which makes a current because the charge is moving through that wire. This is hopefully what you saw in that Faraday's law simulation. But the summary of this, in other words, move a magnet near a coil, and that makes a current. So that's really what I want you to know, is if you spin a magnet, if you move it backwards and forth, if you slide it through a coil, if you just shake it nearby, any of those things, if you're moving a magnet near a coil of wire, you're generating a current. If you've ever had one of those flashlights that you can spin the handle to charge it up, or you can shake it to charge it up, what you're doing is spinning or shaking a magnet and using that to charge a battery, because you're making a current which can be used to charge a battery. So now electric signals, this is another place where I'm going to be very hand wavy and kind of big picture, because I want to get the main idea across and not worry about how the electric signal's actually represented. So for a second here, imagine that you have a magnet next to a wire. So I've got a coil of wire here, and then we've just got a magnet right next to it. So it's got a north end and a south end. Now imagine flipping it back and forth. This coil of wire, if you flip that magnet, you'll change the magnetic field inside this coil, which will in turn create a voltage, which will in turn create current. And so basically every time you flip this, you'll have some electric charge move through this coil of wire. Okay? So now imagine just you're counting every second and you're saying, is it flipped this second or is it not flipped this second? So you're just looking in your wire and saying every second, am I getting current? Am I not getting current? Am I getting current? Am I not getting current? And this is basically a way you could store zeros and ones. If you flip during that second, that means you're sending a 1. If you don't flip during that second, you're sending a 0. And then the next second, you decide to flip or not flip. So you might do flip, flip, no flip, flip. That would represent 1, 1, 0, 1. And so over time, the computer or whatever's on the other end of the wire can look at whether this current is coming through or not and understand what it's looking for. So what I'm saying there is by flipping or not flipping, you can send 1s and 0s through that wire. And so that's not, like I said, that's not how we actually send electric signals, but it gives you an idea that by doing some clever stuff with magnets and wires, you could send a signal. And so computers are ultimately, what they're ultimately looking for is patterns in the current and in the voltage. And then it interprets those patterns as either 1s or 0s. So like I said, it's more technically involved than just looking for flips and no flips, but that gives you the idea of you can create a pattern. We do more complex patterns so we can store more data in a more compact way, but that's the general idea behind Faraday's law. So now you know how we can basically send a signal from one place to another inside a computer using electricity.